All right, so we're going to look at 5.3 complex zeros. And our zeros are complex numbers in the form of a plus bi, where a is the real number and bi is the imaginary number. So therefore, we can now say that every polynomial of degree n has n zeros. Now we have what's known as the complex conjugate pair theorem, which basically states that if you have an a plus bi, you have to have an a minus bi. I'm not too big on this notation with the r and the r bar on the top. Just know that you can't have one without the other. So the author will use this theorem to try to give you trick questions. He'll say, find a polynomial function of degree 4, so that's got to be x to the 4th power, whose coefficients are real numbers and has the zeros of 1, 1, and -4 plus I. What happens is people see, oh, 4th degree, I have to have 4 numbers, and they're going to go x equals 1, x equals 1, x equals -4, and x equals I. That's not the case. At this point right here in your notes, I'll agree with this point right to here. Do not write anything with i's after that. I do not like what the author does. All right, and I'm going to show you an easier way to do this, which will cut your work in half. I agree with what we have to do. We have to take and set these equal to 0 to build binomials for our rational zeros. And here's what the author is going to do, which I don't want you to write down. Do not write this down. You'll see this is crazy. There's no way I'm going to do that much work. He sets all of these equal to 0 and has the gall to still call these binomial factors. How can they be a binomial when there's 3 terms? And what he's doing is he's considering this 4 minus I as one complex number. But it's made up of 2 terms. Don't write this down. Write this down. We're going to have to FOIL these 2 together. Don't write this down. You're going to FOIL that to get this. I don't want you to write this down. Watch the FOILing process. 3 by 3. 3 terms times 3 terms gives you a polynomial with 9 terms. That's way too much work. We are not going to do all that work with these I terms. I will do this because that's rational and we're used to doing that. Here's an alternative. Take your x minus 4 plus I and x equals -4 minus I and write it with a plus or minus sign. What I don't like what the author is doing here is he's insinuating that, oh, we're working the factoring process backwards. You've never factored a polynomial and had an I in the answer. You get i's when you solve by completing the square. So we should do the completing the square process backwards. So when you solve by completing the square, the last thing you did is you moved over the 4 and subtracted it. Okay, we're going to move it back. We want to get the I by itself. We want this plus or minus concept by itself. We know that if you square an I, that it turns into a -1. If you square a plus or minus, it's a positive, so it's pointless. So we're going to square both sides, and we're going to get -1 on the right side. And when you square a binomial, it's always x squared in the front, 4 squared in the back, and your middle term is always x times 4, which is 4x, and you double it because there's 2 middle terms that are 4x. So we can kind of do this in between our ears. X squared, 4x doubled to 8x, 4 squared, 16. Add over the 1, 17. This is what we now have to multiply together. Okay, we don't have a choice. We have to multiply these 2 trinomials together. What I'm stating to the author, don't multiply 2 sets of trinomials. Only multiply 1. Cut your work in half. All right, so I don't have enough room here right now, but you should on your notes. We're going to multiply these 2 trinomials together. And what I like to do is you could use arrows. The only problem is when you get to the third term, you have no arrow space. You can't go over or top because you mix them up. So what I like to do is write it like a 3-digit number times a 3-digit number. Write it down vertically. Take the 17 and multiply it to the 1, to the negative 2x, and to the x squared. Just as if you take the digit in the ones place and you multiply it to all the place values. The best thing here, there's no carryovers. So 17 times 1 is going to be 17. 17 times negative 2x is negative 34x. 17 times x squared, 17x squared. Now, if you want to put a 0 here, you can. It's not necessary. But now take your 8x and multiply it to all 3 terms. And as you find these products, start lining up your like terms vertically. 8x times 1, 8x, 8x times negative 2x, negative 16x squared, 8x times x cubed, 8x cubed. Doesn't have a like term, you just bump it up to the left, just like you did with digits. X squared, again, if you want to put in 2 zeros here, you can, but x squared is going to be multiplied to all 3 terms. X squared times 1 is x squared, line it up underneath your x squared terms. X squared times negative 2x is negative 2x cubed, line it up under the 8x cubed. X squared times x squared, x to the 4th, move it out to the front. Combine like terms. They're already in columns for you. You don't have to search for them when you multiply left and right and you use your arrows. You got to go find them all. They're all lined up for you. There's your function. You're done. All right. Now, you can also use that same technique. Okay, so if you got a little extra space there in your notes, or if you want to put this if you want to put this off to the side or use the back page, but I just, whoops, where's my iPad here? I wanted to bring in my iPad here and say that technique that I just did with the imaginary numbers, are you kidding me? Also works with irrational numbers. So, and I'm not going to do the trinomial multiplication. I just want to show you the setup again so you can see how to get to your trinomials from these crazy problems. So if you had to write a polynomial of a function with zeros, 1 plus square root of 3, 1 minus square root of 3, and 2 plus 3i. Again, what we want to do is you want to take these two right here and write it as x equals 1 plus or minus the square root of 3. Remember over here, you have to have the conjugate cousin, 1 minus 3i. These two come together as x equals 2 plus or minus 3i. So, same technique. Get the plus or minus term by itself. So let's subtract over the 1. Just like we did over here, we'd subtract over the 2. Get the plus or minus term by itself. And again, we're going to square both sides. So when you square a square root, it's just 3. Your binomial squared, x squared plus 1, x times negative 1 is negative 1x, double it, minus 2x. Over here, again, square both sides. Now you square the 3, it's 9. You square the I is negative 1, so that makes it a negative 9. Binomial squared, x squared is x squared. 2 squared is positive 4. X times a negative 2 is negative 2x, double it, so it's minus 4x. You can add over the 9. There's one trinomial. Come back over here, subtract over the 3. x squared minus 2x minus 2 is my second trinomial. And now we multiply those together like we did at the end of that problem. And now you can write a polynomial function given rational zeros, irrational zeros, or complex zeros.